Recording is rolling. Today is Wednesday, October 5th, and we're officially beginning Unit 3. Now, Unit 3 is kind of a hodgepodge of topics that I didn't always teach us by different. Oh, the concept. All right, recording is resumed. All right, so here, guys, full focus right here. Guys, I need your full focus for a few minutes here because there's a lot of thinking that goes into. Well, it's gonna be like okay. All right, so. Yeah, different textbooks have different philosophies about how to teach us exactly. I've come around to AP style. I think it's good for a few reasons. So it's gonna go like this. We're gonna do a centripetal force lab today, right? There's a force that causes like a change in direction. This is the first time we're starting to address this. Like, what's the force that could keep something in a circle, right? We're also gonna look at universal gravitation, right? So masses gravitationally attract from a physics 1 perspective. Then we're going to put those two ideas together and make orbits. Okay, you guys got that? Right. And yeah, so that's how we're doing this. This Unit 3 by AP's book. Right. You guys remember the end of this week is the end of the first quarter. So guys, double check focus, make sure you got everything in. Almost everybody's turn in the quiz that was due in this class. If you have, then your grade is already in the grade book, so that's good to go. There's no school on Monday. Wednesday is the PSAT, and I'm slated to proctor that one. So I don't know where you guys are supposed to be relocated, but just FYI, that's coming up. Yeah, so we got some choppy days coming up. Then there's this. You guys know how the school's going to give everybody a laptop? Okay, so there's this one-to-one device agreement. They did not give me enough for everybody in this class, so I need to go make some more copies of this. But just FYI, I've got that, and I will give that to you guys soon. And they do want that by next Friday, so I just have to make some extra copies. Okay, all right, guys, good so far? All right. Oh, speaking of new stuff, you guys have on your desk a new page. You guys see a page looks like this. That's chapter 7. Okay, so here's what we're doing from this. I'm eventually going to assign you guys these problems right here. This is all being recorded, so you guys got that. But we're going to put that to the side for now. But just so you guys have that paper, if you wanted to read ahead a little bit, right, that's what's going on there. Okay. Oh, AP Unit 3 progress check has been open for a few days. Actually, a lot of the materials for this this upcoming unit have been open on Google Classroom for a few days. Okay. Okay. So put that to the side. All right, we'll worry about this another day. But we're gonna full focus on this this lab today. Okay. All right. So, like I said, we're finally getting into addressing like changes in direction, because you guys remember Newton's laws of motion, which we just covered in dynamics. First law of motion says object rest will stay at rest. An object in motion will maintain its velocity, which is speed, but also direction motion, unless there's an outside force acting on it. Right? Now, you guys know if you put a force on something, it can cause something to speed up or slow down, like in a linear sense, right? We did take that to 2 dimensions with projectiles, but what about like going around a curve, like a car going around a curve, or maybe like a planet orbiting a star, something like that? So the force that will hold something in a circle is called a centripetal force, right? And we need some kind of expression that's going to we can put into a formula so we can calculate a centripetal force, right? How much force are we talking about, right? Guys get this? Right, so I wonder what variables could be at play. And here's here. Let me show you guys the physical setup so you guys know what diagram you're looking at here. Right, I have a PVC pipe. You guys see this PVC pipe? Okay. Those are all around lab station. That's this guy right here, right? PVC pipe, right? Hollow pipe. Okay. It's got a string going through it. You guys see a string? Ooh, look at that. Right, string going through this PVC pipe. And at the two ends are a couple of Play-Doh canisters. I have small ones, I have big ones. These are a couple of small ones right here, but you know, there's a mix in the back, right? Small ones, big ones. Okay. Ooh, this one's really heavy. This orange one's really heavy. This green one, it's kind of light. Right? There's reason to set it up that way. Right? Okay, so you guys get the setup, right? Okay. Kind of this for you guys too, but here's what we do. I'm gonna have the heavy one hanging down and the light one swinging around, just as a practical matter. It works that way. Okay, and I'm gonna swing this around in a circle. Okay. Now, do you guys think if well, let's play around with this just in our minds a little bit. Right? What if I swung this like faster? Do you think the size of the circle would get bigger? Right? As maybe the swing mass would have like more momentum. Like tangential to the motion to like pull this out? Huh, right? Or if I swing it too slow, do you think the size of the circle is going to shrink? Right? And what all variables could we be juggling all together? Well, maybe the swinging canister has some math that I care about. Right? Math and could be kilograms or grams. Right? Probably grams is a good scale for today, but kilograms in general, right? So math swinging around, right? It could be go around at some speed, v, right? Now v could be referred to like an instantaneous speed, right? Like the magnitude of velocity, right? Now velocity is always changing because the direction is always changing, right? But maybe the speed could be relatively constant, right? Like speedometer on a car. Is that okay? Okay. Guys good so far? Okay. There could be set up some circle with some radial size, r, right? The r could be radius, the radial size of the circle, right? And there won't be a true equilibrium on this hanging canister. There will always be a net force. There is always a net centripetal force pulling in. But sometimes a term you hear, now this is a little bit sloshy, like dynamic equilibrium, which is not true equilibrium, but it's just saying like the size of the circle is not changing. Do you think you could swing this around at just some perfect speed so that this radial size doesn't increase or decrease? It just kind of hangs out, right? Okay, right. And then what is that force that's holding this in? Well, it's probably the tension in the string, which is equivalent to and provided by the weight of the hanging canister. Right? I labeled this F for force, like a hanging weight. Okay, so the one that's swinging, I care about the mass. The one that's hanging, I care about the weight. Right? Okay, you guys care about that? Okay. And there's some expression that there's some relationship among these four variables. Okay. You guys got that so far? You guys got that premise? Okay. And that's the question that you guys are trying to get at is what's the relationship among those variables? How can we put these all together in one expression? It ends up being a real simple, straightforward expression, but you guys are going to figure this out. Now, just like normal in science, if you can just deal with two variables at a time, that's ideal, right? One independent, one dependent variable, right? Now, it could have you guys sit down and think about this problem for like 2 weeks, think really hard on this, but we don't have time, so let's move on. I really debated with myself, should I give you guys the printed pages on your desk or not? So I did go ahead not to do that because it's streamlined this and leads you like straight to like how to solve this, right? But definitely have your brains turn on maximum and think like, if I were to design this from scratch, like how would I eventually come to like this particular design? Is it working out? We're going to relate everything to speed. Is it working this way in the end? Right. We're going to do speed versus the hanging weight. Now that's controlling for the radial size and the swinging mass, right? That's that one. You might be in that group. You might be in a group that's doing this, or you might be in a group that's testing this. What's the speed versus the swinging mass? You could change out different masses of the swinging canister to see what speed's going to be equilibrium. But if you do that one, you're also going to control for the radial size. So you use the same radial size of the circle every round, right? You'll also control for the hanging weight, right? So this weight will be the same every time. You guys got that? Or you might be in this third group, speed versus radial size, where you'll try out different radial sizes. So what if I, let a larger size circle develop or a smaller size circle, right? But if you're in that group, you're not going to change out the either of these canisters at all. So it'll be the same mass over and over and the same weight over and over. Okay, you guys got that? Okay. Now there is a scale back there, so if you want to get like accurate values for these, you could. But if you have trouble accessing that, here, you can use this as a kind of a rule of thumb. The small canister is just an empty canister. It's about 6 grams of mass. And the larger, like standard size Play-Doh canister is about double that. Okay. I guess you throw on a tape, it's going to increase that a little bit. Right. But you can also take these lab weights. You can load some lab weights in here. Okay. Have a lab weight in here. Yeah, there we go. Right. See like see this 20-gram lab weight, 20 grams. Pop 20 grams. Okay. And put the string here. Pop on the lid. That should be good. If you think there's too much mass or you're not sure if it's secure, take some tape. There's a bunch of tape back in lab areas. Throw some tape around it. You guys got that? Okay. All right. Let me demo this for you guys. Right. So if you're watching this video, I'm just going to do this as a live demo. Right. Take this whole apparatus. Right. You guys ready to go? Okay. All right. So here's what this is going to look like. It'll look like this, right? See how I've got like a stable size circle up here? Right. Now, how can I get the speed of this thing? Well, maybe it might have something to do with counting like how far it goes and how much time, right? Wouldn't that be true? Right. Do you guys bring your stopwatches today? You guys brought your cell phones for stopwatches, right? Right. So here's what I do. This makes it clear in a minute. I'm going to count off 10 revolutions, and let's say you're timing this. And we're going to count how much time for 10 revolutions. You guys got that idea? Right. So it's this. Here we go. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then when I say 10, you stop the stopwatch, and then so many seconds have elapsed. You guys got that? You guys know you're going to start with 0, right? You start at 0 and then start counting, right? 0, 1, 2, 3, 4, 5. Right. When you say 0, you start the stopwatch. Okay. Right. Questions so far? Okay. All right. Let's take a look at these pages because there's actually 4 different papers floating around. Right. One for each of the experiments, and there's a blank page, which is kind of like a wild card. You can really use it for any of them. All right. So let's go with start with this one here. Okay. If you have this paper with the hash marks cut in the middle and the first two, let's go across the papers because everybody has the same table, but some of these I control different variables for. Okay. There's the mass hanging in grams. There's the weight hanging in millinewtons. Guys, how do you go from mass to weight? You multiply by 10 meters per second squared. You guys can do that, right? Right. Now, normally it's from kilograms to newtons, but grams to millinewtons would be the exact same conversion, right? Just multiply by 9.8 or 10. Is that okay? So, for example, if it was like 50 grams hanging, you could multiply that by 10 and get like 500 millinewtons. 50 times 10 is 500 millinewtons, right? Okay. Right. And notice that one's bold. It's bold because it's one of these variables that you care about that you're trying to measure, right? Is that okay? Right. The hanging weight's a force. Okay. Right. Measured in millinewtons. True. Right. Then you're going to measure mass swinging. So that could also be in grams, and that by itself is bold because you care about the mass of the one that's swinging, right? Right. By the way, if you see just the word mass out of context in this lab, do you think it refers to the swinging one, not the hanging one? Right? Because you care about the mass swinging, right? Right. So that could just be in grams. Right. This next column, take the reciprocal of that. It's not going to make sense now. It'll make sense by the end. Okay. And then the third variable you care about, radius. Go ahead and do meters. So there's a bunch of meter sticks back there. Do you think you could sort of estimate the radial size of that circle? Right. Next column, take the reciprocal of that. This makes sense in the end. Right. A couple of time columns in seconds. Time sub 10. What do you think time sub 10 refers to?
Time for 10 revolutions.
There you go. Time for 10 revolutions, right? Just like I did know, right? You can say maybe it's like 8.5 seconds, right? Time sub 1. What do you think that refers to? Time for 1 revolution. Are you going to take your time sub 10 and just divide by 10? Yeah, that's what you do, right? Now, why would you do that? Why not just go like start, stop, and just try to get 1?
Then it would be more precise.
Yeah, more accuracy, better. More reliable data, right? If you do 10 and divide by 10, the error of when exactly to start and stop the stopwatch also gets divided by 10, so you get much more accurate data that way, right? Right, you guys get that? Okay. So you can say reduce experimental error if that came up with an AP question. Okay. And finally, the last 2 columns, v and v squared. Right, so v that could be instantaneous speed, right? No sense saying speed and not velocity because the direction is always changing, right? But the speed could be pretty well constant, right? Okay. Now, speed, could that be some kind of distance divided by time? Hey, what's the distance around a circle?
2 pi r.
2 pi r, right? Circumference equals 2 pi r, right? Look at this expression right here. I tell you exactly how to calculate it. 2 pi r divided by t sub 1. Oh, that's 1 circumference and the time for 1 revolution, right? 1 circumference in 1 time period. Wouldn't that give you the speed, right? Right. And then it should have made that one bold too, but as a sort of like a dependent variable, sort of, right? And then the last column, b squared. So go ahead and square it. You guys know all along this class, even since the very first week of this class, you guys have been doing variable manipulation, axis manipulation. Let me pause this real fast. Pause. All right, recording is resumed. Oh, yeah, go ahead, just in case. Yeah. All right. So what I want to say about this is here, you can kind of look ahead. Let's look at these graphs. One says, actually, let me go back and do the part skip. See the hash marks? The hash marks means you're controlling for that variable. So if you have this page, see how you're changing out the weight every time, but you're controlling for the swinging mass and the radial size? And you're going to let the speed naturally be whatever it is. You guys see that? So sort of like independent, dependent variable, so sort of that mindset, right? If you have the paper with the split hash marks, see where it's like split hash marks, right? You're changing out the swinging mass every time, but you're controlling for the hanging weight and the radial size. and then just let the speed be whatever it naturally is. Okay, so it's like independent, dependent variable. You guys get that? Questions so far? If you have this paper with the hash marks all the way on the left, oh, well, that means you're controlling the two canisters, so you're not changing out anything to do with the weights in the canisters at all. But maybe you'll set up different size circles, right? Okay. And then maybe for the bigger circles, might have to swing a little slower, vice versa, right? And then just see how it naturally comes out. Okay. Right. Oh, you might have this one, which is completely blank. Now that's sort of like a wild card, right? You just pick one of those 3 labs and then just kind of fill in from there, right? So you have to more figure it out on your own, right? Which is more, maybe I should have given everybody this one, so you take more thinking on your part, like what exactly can I do? Because you're going to do one of these 3 experiments and only one of these 3, right? Then we're going to come together as a class and put all this data together. Now these graphs down here at the bottom, some of them say borrow data to complete this graph. That means if you have that particular paper, you can't put it together just based on that data because you're controlled for variables. But the one that's completely open, like blank, you could graph that. Right, you guys got that? Right. And then since there are 3 different types of lab papers going around, right, we'll collectively be able to put all these graphs together, right, as a class. You guys got that? Right. Then on the back side, see where there's 3 big graphs, right? This is like where it's coming down to the finish. They all say v squared versus something, v squared versus something, v squared versus something, just because I know how this eventually goes together. So this is going to lead straight into the formula, right? It's axis manipulation, and I'm telling you guys ahead of time. Now, by the time you guys get to the actual AP exam in May, you will have known this formula. You will have applied this formula lots of times. By the way, you guys see number 27 on your homework? Looks a lot like today's lab setup. Ooh, so you might have to take this this equation that we get out of this lab and apply it to something like that, right? Okay. And then you would say, okay, well, I know that blah, 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 what these graphs would look like, having that knowledge, right? Okay, you guys good so far? All right, so a few more things here. One is that this is one of those labs that if you're really careful and meticulous about the data, especially like getting the stopwatch exactly right and getting the radial sides exactly right and controlling for everything, right? That the graphs come out really nice. But if you're kind of sloppy with stuff or don't do things exactly right, then the graphs are all over the place. They don't make any sense. Okay, so if you do everything right, the graph's gonna look good. Okay. Oh, speaking of which, here's something I always see. Okay, so when you're swinging this around, do you want to right here grab the bottom one and hold it in place with your hand? Do you want to do that?
No.
No, because that wouldn't make any sense. Because now you're applying an extra force that's throwing all your data out of whack. The purpose of the hanging weight is to naturally provide what would be the centripetal force that's going to hold everything into place, right? Okay, that. Okay. All right, and then since you guys are AP, I'm going to have you guys do one of these classic 5-part write-ups. So I'm going to leave this on the projection during class. Actually, what we'll have to do is that tomorrow we're going to put the graphs together, and I have an AP style rubric, and we'll pull that up, and I'll have you guys grade your 5-part write-up. Okay. All right, I think I told you everything I need to tell you. So you're going to get all your data today. Tomorrow we'll put the graphs together as a class, whatever ones that you couldn't do because you didn't have the data yourselves with your teammates. And then we'll go over the rubric for this 5-part write-up. Okay? All right, you guys good to go? All right, you guys got the rest of the class to get your data and do whatever graphs you can do. And I will walk around and help you guys out.